So last time we talked about contracts, what you can do with contracts, and how there are some interesting questions about some of the details of how contracts work. Today, we're going to look at formalizing the semantics of contracts in a core calculus, and then we're going to see how we can use that calculus to answer some of these questions and come up with some criteria that we want for a contract system and determine whether various contract system formulations that we might have do the right thing and produce the answers that we want and have the properties that we want. So today's going to be all on the whiteboard. If you can't read something that I've written or you can't make something out in the back, please say something. Yesterday, everybody was very good about asking lots of questions, so I hope that will continue today. So this is the outline for what we're going to talk about today. We're going to start with classic programming language, PCF. And then we're going to extend that language with contracts and see what the semantics of contracts are. Then we're going to look at some interesting examples and how the semantics sheds light on those examples. Then we're going to look at a concept of ownership and how we can formalize that in our language, and then use that concept of ownership to describe and state an interesting property of the contract system and see whether it holds depending on some choices we might make about that contract system. Okay. So, any questions people might have before we start from yesterday, etc.? Okay. So let's start with PCF. So PCF is a classic programming language. For PCF stands for Programming with Computable Functions. It's originally invented by Gordon Plotkin for understanding the semantics of programming languages. Plotkin used it to compare a variety of ways of formulating the semantics of programming languages along the lines that David talked about in his talk yesterday about different ways of formalizing semantics. But fundamentally, it's sort of a core typed lambda calculus that looks something like this. We'll start with the expressions. Expressions in PCF are either values, variables, applications, recursion, some operation, or an infix operation, or a conditional. So here we've modified the original PCF slightly to have a normal conditional. I think Plotkin's original PCF tested whether the first expression evaluated to 0, but that's annoying. Yeah. Indeed, I don't. That's because lambdas are values. So our values are our base values, which will include Booleans. and numbers. And our values are base values or our lambda abstractions. So far, so good. So now let's look at types. Types are simple in this language. Either base type, I'll just Boolean, or number, and function types. So this should all be totally familiar from earlier this week. But now I want to present the type system and operational semantics. And I'm going to present the operational semantics in a reduction semantics style, the way David described yesterday. But let's start with the type system, because that's easy. So our type system judgment looks like this. And we'll say that there's our rule for lambda. For variables, for application, there's if, and then the most interesting rule, I think, I'm going to leave out operations which are boring, and most interesting rule is for recursion, says that looks a lot like the lambda rule. So there we have our type system for PCF. So far, so good. Now let's look at the operational semantics. Any questions about the type system?
Yeah, about the recursive rule, shouldn't it be how and
Yes, that should be tau. Any other questions? Okay, yeah. Yes, I will try to write bigger. Do you want me to rewrite that bigger? Okay. So the operational semantics is going to be formulated in terms of evaluation contexts, like we saw last time. So we need to give a definition of the evaluation contexts, for which we're going to use capital E. We're going to give a grammar of evaluation contexts. An evaluation context can be a whole, or we can evaluate in the operator of an application or in the operand of an application if we've already evaluated the operator to a value. We can evaluate in the test position of an if. We can evaluate the parts of an operation. Is this easier to read? Okay. So that's our evaluation contexts. So this just tells us where we're going to be allowed to do evaluation. And so this says we always evaluate the operator before the operand because we're allowed to evaluate over here when this is just a plain expression, but we're not allowed to evaluate over here unless this is a value. So we have to evaluate the operand, the operator entirely to a value before we're allowed to look at the operand. You can also see, for example, that if behaves normally, there's an evaluation context to evaluate the test, but there's no context on the inside of an if. And so we don't evaluate under if, which hopefully is what you all expect. So now that we've defined that, we can give the appropriate reduction rules for this, which are going to be, which I'm going to specify in 2 steps. I'm going to say there's notion of reduction, and then we're going to lift that to the evaluation contexts. So we will say that we have a rule that an arrow that goes from E to E prime, and then we're going to define a different So note that I've drawn 2 different arrows, one with the little vertical line. And this is going to distinguish reduction from reduction in a context. And this says, and it's useful to make this distinction because it allows us to say some rules apply inside any context. And then if we want to, we can describe some rules that operate only on the whole term, and we will have an example of that. Okay. So what do our rules look like? We have our usual beta rule. We have recursion. That's probably too small to read. We have our usual if rules. Those are all the rules we need. For the moment, I'm, again, leaving out the definitions of operation. Well, I'll write in one op rule, so because it's useful to talk about what's going on in this rule, which looks a little weird. So what's weird about this rule? Yeah? Yeah, it doesn't seem like we've actually done anything. And this is because we're making sort of pervasive use of puns between the syntax of our language, which is just marks on the whiteboard, and the mathematics of the integers, which is a different set of marks on the whiteboard, we're looking at a syntax which includes the natural numbers, and we're omitting the ways in which we would have to explicitly map from natural numbers to terms in PCF, and then extract. What's really going on here is we've got two terms in PCF which are combined to form a bigger term in PCF with this plus sign in it. And then we're extracting the numbers inside that term. We're adding them together, which we denote by writing a plus sign in mathematics font here. And then we're adding them together, and then we're injecting number back into the syntax of PCF. And we're doing all of that extraction and font change and injection implicitly without writing it down. And in a paper, you might see this done by typesetting things slightly differently. I did add more space around this plus over here than this plus over here. Or if you were being particularly pedantic about these things, we could write these injections and projections explicitly, maybe like this, to indicate that inside these little hats are numbers, and the little hats are going from numbers to syntax, and then we've got two numbers, which we can, now that we're over here in number land, we can add them. But I'm going to go back to writing puns everywhere and leave those off. Yeah?
The brackets arrow to notation is just regular substitution?
Yes, this is standard capture avoiding substitution. I'm not sure what notation other people have used for substitution, but substitution is, I think, the thing in programming languages with the most different equivalent notations, just because everyone hates you and wants you to be confused. Yes. Well, how about instead of doing that, I just write it larger? So what this is saying is we're substituting x dot e for x in e, which is how we get recursion. We're substituting the term itself inside the term. We're just substituting v for x in e here. There's another question in the back. Yeah. We could, the thing that's cumbersome here is that I wrote down the reduction rule for plus explicitly. And usually, if you're writing a semantics for a large language with a lot of operators, then you'll defer this to some specific relation for the arithmetic operations. And in fact, this is what David did yesterday in his presentation. He had a notion of reduction A that was for arithmetic, and that was where you just wrote down the big list of arithmetic rules. But ultimately, there's no way of getting around writing down the rules for all the operations. Whether what you're doing is describing the semantics of a programming language or implementing a compiler or implementing the x86 processor in your laptop, you got to have a case for all of the operations, and there are a lot of them, and that's just life. Any more questions? Yeah.
So I'm still confused about the context in general. I don't really see why we need this context.
Okay, that's a great question. So let's look at contexts and how we use this rule to describe the reduction of a program. Can you read over here? Okay, so let's think about the following program. Okay, so here we have a program which is the identity function applied to the constant function that produces 1 applied to 2. And I've left out the types because they're not really going to be interesting here. So let's look at the reduction relation that we've defined. We've defined two relations that are about reduction. This one and this one. So does this relation apply to this term? So let me label these rules. So which rule applies? Okay, so the beta rule says we can take something of the form lambda x applied to a value and reduce it to something else. Now, is this term of that form? Okay, so that means which is the lambda? Okay, so here's the lambda. That does indeed look like it matches lambda x dot e. Okay, so now we need a value. So is this a value? How many people think this is a value? Okay. Unfortunately, that's a bad sign. Democracy wins. So if we look at our grammar of values again, there's our grammar of values. It says values are either base values or lambda abstractions. And this is not either one of those. No, this says lambda x1 applied to 2. As I love my parentheses, but I think this is enough parentheses for this term. But if people really want extra parentheses, that's why there's a big space there. Yeah, yeah. Edwin is here after all. Okay, so I'll use red parentheses for ones that aren't really necessary. So here we have, now that we've parenthesized this more, it's definitely not a value. And let's think about so that means we can't apply beta, and pretty sure that none of the other rules are going to apply. So what can we do? So let's hope we can apply this rule, because otherwise we're going to be out of luck, since we can't apply this reduction rule. So that means we need to be able to decompose this term on the left, the one I've written there, into some big capital E and some little e where we can reduce. And you can probably guess that the term we're going to want to reduce is this one. So that means we need to figure out so little e is going to be this. So big E is going to need to be a context that includes this applied to something. And then we're going to put this term in that something. So let's just say so this is going to be little e, and big E is going to be the identity function applied to a whole. And we'll see that this matches up with our grammar, because we've got v, the identity function, applied to e, and then e can be whole. So now that we've said this term is equal to capital E with little e in the whole, right? So and we know that this little e steps to 1 by beta. Then, therefore, this term steps to capital E with 1 in the whole, right? Which is equal to lambda x dot x applied to 1. Maintain my convention here. And then we can do this again. If we want to break this up into a context and a term that can reduce, a redex, what's the redex going to be? Yeah, so now we can use the beta rule. So how much of this term is the beta rule going to work on? All of it. So then what do we want to have? How big a context do we want to have? An empty context. So now we decompose this into, so now our context, I'll erase, now our little e is going to be lambda xx applied to 1, and our context is just going to be a whole, an empty context. And then this steps to 1, and therefore e with e in the whole steps to the empty context with 1 in the whole, which is just 1, and we're done. So that's how you use the evaluation context style semantics to reduce programs. And we didn't have to write structural rules to say we can perform beta at inside various other terms. All of those structural rules are captured in this one rule. Okay.
You didn't really need the evaluation context for the second.
So if what we want to do is say that the whole term, our whole original term, reduces in 2 steps to 1, then the relation that reduces it in 2 steps is this relation, and this relation is about terms in context. So we can't not use the evaluation contexts. It happens that the particular evaluation context that we used in the second case, in the second step, was the empty context, but the empty context is a perfectly good context that we can use, just like the empty list is a perfectly good list.
So in the second case, that rule simplifies to, if E single arrow goes to E prime, then E arrow with a tail goes to E prime. Is that what it says?
So if you have it's the case that this relation includes this relation because the empty context exists. So if all your reductions happen in the empty context, then that's fine. But this is a strictly bigger relation because it allows you to do reduction in context rather than just at the top level of your term. Yeah?
There is a relation that maps the evaluation context with the term curtain to a simplified term. So on the right hand side, you have E1 mapping to gamma x or x.
So this is another what says that we can. This grammar is just a grammar for terms with these funny square bracket things. What's this plugging and decomposing thing? Is that what you're asking? So yes, this is another example of helpful conventions that we leave out so as to be extra confusing. And we can write down, although I'm not going to here, plug and a plug rule that takes a context and a term and produces a bigger term by putting the term where the hole is in the context. But usually we think of evaluation context defined this way as being terms with holes in them, and this syntax as meaning plug the term into the hole producing a bigger term. And we sort of leave that implicit. So this is you can think of this as a grammar for term to term, a specific set of term to term functions, if you want. You had a question? Okay.
So the last one is a value or?
One is a value.
Or the context with a value?
When you take some term and you plug it into the empty context, you get the same thing back. That's what the empty. What? So that's the same as the sort of general rule for plugging terms into contexts. Okay. However, I've now used half my time and we haven't seen any contracts. So I want to now move into looking at the semantics for contract PCF. So let's let's start by looking at the syntax. So the syntax for CPCF, we're going to add a few things to each production. We're going to add a type constructor for contracts that monitor values of type tau. We're going to add a contract monitoring form, which is going to apply a contract to an expression. I'm going to use K for contract. We're going to add a grammar for contracts, which is, it's called flat contracts, which just have a term that's going to be a predicate, or we're going to have function contracts, or we're going to have dependent function contracts. However, there's one really important thing that I've left out from this syntax, which is labels on our monitors. Because the key thing about contracts, something mentioned last time, is that they're agreements between people. And we're going to denote who those people are that are agreeing to the contracts by labels on these monitors. So we're going to have two labels on the monitor for the two different people that agree to the contract. And then there's going to be a third label, actually, I'm going to put here, which is where the contract is from. Because we've got both the parties that agreed to the contract and the person who wrote the contract. And as we saw last time, the contract contains arbitrary computational power, and in particular can misuse values that it has access to in the dependent case for contracts. Get this value, you can misuse it, and so we need to be able to talk about the author of the contract as a person who could potentially misuse values and therefore need to be blamed. So there's our syntax for contracts. Now let's add to our type system. So the type rules, very straightforward. So you can see a few things here. One is that you check that the contracts are for a particular type of term. We could have integer contracts or integer to integer contracts. But contracts are not reflected in the type of the term. You can't tell statically that something has been contracted. And then we have types for our contracts. there's our typing rule for function contracts, which allows us to compose two contracts. And then the most interesting typing rule for contracts is for dependent contracts, which looks a lot like the function contract rule. Except we extend the environment for typing K2. You can see here, dependent contracts can refer to a term of type T1 that is the value that we have here. So there's our typing rules. And yeah?
You need an annotation on the bound variable there. This is your grammar too.
Yes. Okay, so now let's look at the operational semantics for these terms. So in order to specify the operational semantics, I'm going to actually add a couple additional terms that we don't have in our source programs. And I'm going to add some evaluation contexts. Let's look at the evaluation contexts first. We can evaluate the predicate in a flat contract, and we can evaluate the term we're going to check. So now let me talk about the two additional expressions that I'm going to add, which, where should I write them? I'll write them over here. We've got two additional expressions, which I'm going to say are, sure, this first one we're only going to need later on, but we'll see the reason why we need it later on. This says, the check form says, run this expression, and if it produces true, produce V, otherwise produce a contract error. And this is going to have some labels for which error to produce. The other thing we're going to add is an error, which says raise a contract error and blame label K. That's the person who violated the contract. And which contract was it? It was the contract labeled L. So those are things that we saw yesterday when we saw contract error messages, and we're going to have those as well. And now that we've added that, we're going to have one additional valuation context, which is check, can evaluate the term in a check.
Question.
Yeah.
In
Yeah.
Does the k variable mean that we don't look inside k for regex?
Right. Yeah. Contracts. We don't need to look inside k for regex. I think is that right? Yeah.
But since we have an evaluation context for flat, does that mean that that only gets evaluated in the check form?
No, I'm. Where did I put my notes? Yeah, this is actually, I'm actually should not have added this evaluation context. Just gonna pretend that doesn't exist. Okay, so there we have our evaluation contexts, and we're only going to evaluate contracts inside the check form. So now we can add some new reduction rules. The simplest is for flat contracts. So if we have a monitor of a flat contract on a value, then this is going to reduce to this check form. Now we already see something interesting here, which is that one of our blame labels disappeared. So why do we no longer need the blame? So one thing to remember, two blame labels, those refer to the two parties that agree to this. In a monitor, which party is which? K is the person providing the value, and L is the person receiving the value. Here, the context for expression. So this label L is for the context, and it's not over here. So why don't we need L anymore? Yeah. So what do you mean by assumes that we have no surrounding context? Yeah, so flat contracts are just predicates. That's why we're just applying this function to V and seeing what answer we get. But yeah, so I think you're on the right track here. Anyone else have thoughts on what's going on here? Why don't we need to worry about the label for the context anymore? Yeah. So the important thing here is that once we've checked a predicate on a value, if it succeeds, we're good. If it doesn't succeed, we're going to blame K. But either way, we've got just a predicate that we're asking yes or no. So there's no way that, whether it says yes or no, there's no way that it's the context's responsibility for that result. So we can't possibly blame the context, and so we don't even need to remember it anymore. So now, let me add the reduction rule for check, or rules for check, just so we see how that works. So if we evaluate our check to true, then we're just done. We get that value back. If we evaluate our check to false, we get an error, contract error with the appropriate blame labels. So now we've seen how flat contracts work. Now let's get into the interesting stuff where we have higher order contracts. So the first rule is for plain function contracts. I want to be able to put this up higher. I'll write it here and then I'll write it again, perhaps. So we've got some value, which is being monitored with a function contract. And what we're going to do is we're going to produce a new function that's going to do this checking internally. And this is the key insight for how to implement higher order function contracts. So there's the rule, and I'm going to rewrite this rule over here slightly larger because this is maybe the most important thing to learn about the semantics of contracts. I'll pick a different color. Okay, so let's walk through the details of this rule. So that's the full rule. I've left out the blame labels on the right-hand side here. So let's think about this without the blame labels, and then we'll talk about what the blame labels are supposed to be. So we have a function that's supposed to take in things that match K1, produce things that match K2. We want to check that V is actually something like that. We're going to produce a function that it's going to take in some x. Then what it's going to do with that x is we're going to check that it matches K1. Then we're going to apply V to whatever we got back from that check. And then we're going to check that the result of applying V matches K2, which is just what we said we wanted our function to do. So now let's think about the blame labels. So K is the label for the person providing the value. L is the label for the context. So whose responsibility is it to live up to the obligations of K1? The context or the value? Okay, how many people think, let's first have a vote. How many people think K1 is the responsibility of the context? How many people think it's the responsibility of the value? Okay, so it looks like about 10% for each and 80% for I'm scared of answering this question. Which is pretty good. In a lot of my classes, it's 5, 5, 90. So you all are doing pretty well. So let's think about this in a concrete example form. Let's imagine we have the function lambda x, x plus 1. We have the contract, so that's v. We have the contract integer, arrow, integer. And we have the context, which I'll write C, as okay, so our value is something that adds 1. Our contract says integer to integer, and our context applies what we have to 3.5. Who's doing something wrong here? Context, the value. So our contract says, if you give me integers, I'll give you integers. If you give v an integer, is it going to give back an integer? Yes, definitely. Even for floating point, actually, this maintains integerness. But this 3.5 is not an integer. I'm 100% certain of that. So it's the context that's not living up to this. So which part of this contract is going to fail? The domain or the range? The domain is going to fail. So that's this part. Said that this part, K1, is being violated by the context. So K1 is the responsibility of the context to live up to. What about K2? Whose responsibility is it to live up to K2? The value. It's v. So, just like it's the responsibility of v to live up to this whole contract, it's the responsibility of the result of v to live up to K2. So the labels for the whole initial contract are going to be the same as the labels for checking K2. But the labels for checking the argument are going to be different. If we get, let's say K1 was a flat contract, checked for integerness, then we need to take this reduction and blame K here, which is the first label in our monitor. So that means this label should be the label, the outer label should be the label for the context, which is L. K1 comes from the same contract that K1 arrow K2 came from, so that label is going to stay the same. And now X is a value from the context. But now it's the value. Who's responsible for the context that this monitor is going in? What was that? So it's not. So what are we doing with this monitored expression? We're taking it and we're handing it off to what? Handing it off to V, right? We're applying V to this. So we're taking whatever value we get out of this monitored expression and we're giving it to V. So V is the context that this is going into. So now we've swapped the positions of the context and the value because the context is supplying X and it's going into V. So previously, K was responsible for the inside, L was responsible for the outside. But now in here, the outside has become the inside, and V here is the outside that we're going to apply to this. So we need to the new label for the context is K. So we've just swapped these positions. And this is one of the key insights for understanding how contracts work, which is that when you go from first order to higher order, you have to maintain this notion of both the context and the value. And when you pass through to a function, that context and value notions switch because the person who provided the function is now the context for the value that got handed to the function. And the person who was given the function is now the person who's supplying values to the function. So we have to switch. When you have higher order values, that is functions, you're no longer just producing simple values. If I give you a function, you can now give me values by applying that function to them. And if we have further second or third or fourth order functions, we can go back and forth and back and forth. And we're going to switch these labels back and forth and back and forth. So if you supply 3.5, you're failing to live up to that contract. If I wrote this function and you supplied 3, then we're going to 3 will pass the integer contract, but then we'll get 4.5, which will fail the result contract, and it will be the fault of V because this is not a correct function for this. This function does not live up to this contract. And if we add more levels of functions, we can go back and forth yet more times. So let's think about this. I'll write any for the contract that always succeeds. And so let's see what happens here. We apply 3. We hand 3 to v. Okay, so then v gives back a function. So v is responsible for this function living up to this contract, which is k2. Then we supply 2 to this integer contract, which it satisfies. And so then v is responsible for living up to this contract, which is yet again k2. And it fails to satisfy that contract because 2 plus 1.5 is not an integer. And we can further go back and forth. If we take in a function, let's consider the following example. Got a value which is lambda f context, which is and a contract, which is, I'm leaving out the flat constructor. So any is just so let's think about this example, and let's work through what happens when we monitor, when we put a monitor to monitor this contract in this context around this value. So the term we get is, let's say, monitor k, l, j, so let's plug these together and see what happens. What happens here? We first need to check that this value satisfies this whole contract. So then that means we're going to use our function contract reduction rule. So we're going to decompose k into k1 and k2. K1 is odd, arrow odd. Okay, so we're going to monitor odd, arrow odd on lambda yy. Well, first we're going to construct this function that monitors odd, arrow odd on x, then applies v to that, and then monitors any arrow any on the result. So that's what this reduces to in one step. Then we actually, that produces a value. So our monitor produces a value, and then we can take one step of beta reduction, substitutes lambda y in for x here. So then we are monitoring odd arrow odd on lambda y. So that's a function that, but what are the blame labels when we're monitoring odd arrow odd on lambda y? Well, we started with KL, and we're monitoring odd arrow odd on x with LK. So we're swapping them. Then we're monitoring odd on the domain and odd on the range. The range contract is going to be LK, because we've swapped exactly once. The domain contract is back to KL. So what's going to happen when we, first, what's going to happen when we run this program? Is it going to succeed? Is it going to fail? What's the answer going to be? Leaving aside who might get blamed here. Yeah? It's going to fail. Okay. When is it going to fail?
When we're providing the values that we're putting into, and it's
So 2, that seems like a good intuition. 2, there's something wrong with this 2. So it's when we provide this 2 to something that something's going to go wrong. So that's good. So maybe anyone have exactly what's going to go wrong here? We're going to provide 2 to what? We're going to provide 2 to a function that's supposed to be getting odd numbers. And 2 is sadly not an odd number. In particular, what's going to happen is we're going to pass in lambda y for f. We're going to reduce this. The identity function applied to 1 is 1. 1 is not 0. So we're going to produce f, which, unsurprisingly, is the identity function. So this whole thing is going to produce the identity function. Then we're going to apply the identity function to 2. But the identity function that we get back is one that's supposed to be given odd numbers and produce odd numbers. So we're going to produce it, hand it back, and then we're going to apply it to 2. But it's supposed to get odd numbers. It's supposed to return odd numbers. It's not going to do either of those things. We're going to get an error. So let's think about who's going to get blamed for this error, and then we'll be about out of time. So who's going to get blamed for this error? Do we think the context or the value is going to get blamed for this error? So one person says the value. Anyone for the context? Any votes for the context? Okay, a couple votes for the context. So why is it going to be the value?
We pass 2 to the value.
Yeah?
That's where
So the value is responsible for which parts of this contract? This part? This part? Which part of the contract is the value? So let's walk through exactly how this works. So we've got this expression, and we have mon, we have some evaluation context around mon k, l, j. So this is going to reduce to same context with Okay, so that's the first step we're going to take. So we've got V, and it's taking odd to odd. So now the next step we're going to take is we're going to apply this to lambda yy. So we're going to substitute in lambda yy for x. And I'll just write down the resulting term. Okay, so now we can reduce this, because this is our read x, using the function contract rule again. I'll call this bound variable x prime. Okay, so now here's our function that we're going to pass yeah? So I shouldn't really have done this reduction early, but because I did this reduction under this lambda to simplify things. But really we would substitute, really we need to substitute this function in to, this is, I shouldn't have done this reduction here. So that reduction will happen, but only later. So, okay, so here we have this term which we've reduced lambda yy. Now we're going to substitute this in, and we're going to, I'm going to take several steps, which is going to be applying lambda yy to 1, getting back 1. That's going to pass all the contracts. Then we're going to get back this function, and we're going to apply it to 2. No, this is wrong. So very soon David's going to show you a method for not getting this wrong. Thanks to computers. They just get everything else wrong. Okay, so here's our reduction monitoring k applied to v. So we have this. Now we're going to substitute in lambda yy for x, which is going to produce monitor KLJ any to any. And this whole thing is going to be applied to 2. So then we reduce this term. We'll reduce this term to okay, so now our next redex is this application of v to this contracted lambda expression. And v is this term. So we will get this term, we will get if, we're going to reduce this term, which is if, I'll label this v2. So we get if 0 v2 applied to 1, then v2 else v2. So that's what we have here. And then we're going to check that the result is an any-to-any function. Okay, so v2 applied to 1, we're going to substitute in 1 for x prime, which is going to check that 1 is odd, which it is. Apply lambda y to that, which is going to give us 1. Check that that's odd, which it is, and return 1. So this is going to reduce to 1. And so which is not 0, so we're going to produce v2. And so, okay, so this v just goes away. So now we're just left with this term. So we're going to check that this is an any-to-any function with blame labels k and l, and then apply it to 2. So that's going to reduce to lambda x double prime monitoring any with blame labels k and l, and then applying this to x double prime monitored at any with blame labels l and k. All applied to 2. So now we're going to substitute in 2 for x double prime, check that it matches any, which it does. Then we're going to, so we have 2 substituted in for x prime. We're going to check that it matches odd, which it doesn't, and we're going to blame k. So, is that right? Yes. So we're going to blame k, which is the value. So we've, by reducing this, seen that it is in fact the value at fault. The value does not live up to this contract. Now, why doesn't the value live up to this contract? This is the same puzzle that we talked about with the trash compactor last time. We take a function, we promise to only apply it to odd arguments. We give you back a function that you can do anything at all with. But that's not really keeping our promise. We are not taking, if we promise to take care of this function, and then we hand it to you to put in your trash compactor, we are not really taking care of it, even though it's you that's running the trash compactor. We promised not to apply it to any even argument. Then we handed it to someone who did not make that same promise, so we are at fault. And so we can work through our semantics, see that by flipping the blame labels, we eventually get to the answer that describes why the trash compactor puzzle works the way it does. So that's all we have time for today. Next time we're going to see how we can prove that these are the right semantics.